This tutorial is going to demonstrate how to do a one-way repeated measures ANOVA in R. The repeated measures ANOVA is used for analysing data where the same subjects are measured more than once. For example, you might have measured individual self-esteem scores, which would be the outcome or dependent variable, on 3 time points during a specific diet to determine whether their self-esteem improved. A one-way repeated measures ANOVA is an extension of the paired samples t-test for comparing the means of 3 or more levels of a within subjects variable. The assumptions of a within subjects ANOVA are that there are no significant outliers, that the outcome or dependent variable is normally distributed, and that the variance of differences between groups should be equal. So the first thing that we need to do is install and load the packages we need for this tutorial. We will use the Datareum, rstatics and ggpubr packages. To install them, you can simply type install.packages and then in brackets and quotation marks the package name. And then to load them, you can type library and then in brackets the package name. Remember that if you've already installed a package, you do not need to really reinstall it, as the R environment will remember it. But each time you do want to use a package, so for example, if you're starting a new script, you do need to load it in using the library function. For this tutorial, we are going to use the self-esteem data, which is for the Datareum package. This dataset measures self-esteem scores over 3 different time points. And we can use a one-way repeated measures ANOVA to determine whether the mean self-esteem scores are significantly different between these time points. First, we need to convert the data to a data frame and then we can view it. You can convert it to a data frame using the following piece of code below, and then view it using the view function. Remember that view has a capital V. So this is what our data looks like. We have our participant ID numbers, which are repeated because it's a within subjects design. We have the different time points, and we have the self-esteem scores. So before we can run our ANOVA, we first need to check the assumptions. So firstly, let's check that there are no outliers. And we can do this by using the identify outliers function, like this. And here are our results. As you can see, there are no extreme outliers, and we know this because false has been returned in the is extreme column here. The next assumption that we want to check is that our outcome or dependent variable is normally distributed. And we can do this by using the Shapiro-Wilk test, like this. And here are our results. As you can see, all of the self-esteem scores were normally distributed at each time point, as all the p-values are greater than 0.05. But please do remember to check whether your supervisors have different cutoff points. We can also check normality by creating QQ plots. And this is a better method than the Shapiro-Wilk test, especially for larger samples, as the Shapiro-Wilk test can become very sensitive to even a minor deviation from normality. QQ plots draw the correlation between the data and normal distribution, and you can tell you want to do a QQ plot by using the ggqqplot function, like this. And here are our QQ plots. As you can see, all of the points fall approximately along the reference line, so we can assume normality. The final assumption we need to check is that the variance between groups is equal, and this can be done using Mortley's test. However, we do not need to do this prior to running the ANOVA, as it will be automatically computed during this process. And we will be using the getANOVA table function to get our results. And by doing this means that the greenhouse Geyser correction will be automatically applied to any factors violating this assumption. So now we are ready to run the ANOVA, And we can do this by using the ANOVA test function, like this. And here are our results. As you can see, the self-esteem scores were significantly different at different time points, as indicated by the p-value here. And finally, because of our significant finding, we will need to run some post-hoc tests to see where the significant difference lies. For one-way ANOVAs, you can compute multiple pairwise t-test between the levels of a within subject factor. Due to multiple comparisons, we will correct the p-values using Bonferroni correction. You can calculate these comparisons by using the following piece of code. And here are our results. As you can see, all pairwise comparisons are statistically significant, indicated by the p adjustment column here. Here is the full piece of code that I've used in this tutorial for you to copy and have a go with yourself. You can also use it to adapt to your own data.